So yeah, welcome to my presentation. It's about real-time customer engagement with Kafka and Flink. And I would like to start with an out-of-the-ordinary introduction to the topic, so join me in a little thought experiment. So I would like you to imagine that you're driving with your family on the back seat. So you're driving a car and there's lots of traffic on the road. And now what you're doing is you close your eyes. And if you're sitting in the audience, just do it. Just close your eyes and think about how does that feel to close your eyes while you're driving a car? Well, you may open up your eyes again to not fall asleep. And my question is, would you do that in real life? The answer, hopefully, is no, because that would put the lives of your loved ones into danger. But what would you do instead? Instead, you would check the data while it happens to safely drive the car. In fact, what you do is stream processing. So you process the data in motion while it happens to stay safe, right? So this was one of my analogies why stream processing is important, but I have another one. And it's about ice cream and gaming. And I know the weather where you are at the moment is a bit weird to talk about ice cream, but it's okay, stay with me. But what do these two things have in common? So what I can tell is both of them make us happy, right? And I have a little question for you. If you see these two sorts of ice creams, what do you think which one tastes better? I think most certainly it's this one, right? This must taste better. But how do you know? You didn't try the other one. You just decided by the look of it on your first impression. And this is because of the so-called halo effect. So in other words, the first impression counts. The moment the customer enters the shop, the player plays his first session, the user uses your app for the first time, whatever, this moment counts. And in order to make a positive impact, a response needs to happen quickly. And this is also because of the time value of information. Often people do not think about this too much, but I have an example for you. So let's say you have a navigation app and you display traffic data in this navigation app. This traffic data has a very high value when it first arises. So the users want to see what kind of traffic is going on right now. Where's the traffic jam? But the more time passes, the lower the value gets of this information. And this means for us that we need to respond to life as it happens because, and this is one thing you should take out of this talk, because life doesn't happen in batches. And this is a quote from Alan Friedman and Ted Dunning. You should check out the article I linked here below. And this is kind of my little motivation for this talk. And with that, now I would like to introduce myself in the classic way. So my name is Volker. I'm an expert data engineer working at InnoGames in the beautiful city of Hamburg, Germany. And I have two kids. You can see them in the background. This was, by the way, our first family vacation this year. Very exciting. I also like to do photography, and you might have seen it. Not sure if you can see it in the background here. There. I like retro games and consoles. So all the old stuff from the 80s and 90s. I just love that stuff, and I still play with that. I'm also available on LinkedIn if you'd like to connect. So talking about InnoGames, we are a company founded in 2007 and we are creating mobile and browser and cross-platform games. And we have 9 live games so far. And as you can see, this is our portfolio. So we have games in the field of simulation, strategy and RPG. And what do all these games have in common? Well, you might guess they all create lots of data, streams of data, so to speak. And if we talk about streams of data, they are essentially everywhere. So almost everything that you see out there, no matter if it's GPS data, web interaction, game interaction, sensor data, whatsoever, all this is naturally created as a stream of data. And if we talk about stream processing, that means that we process the data in motion happens. And a typical stream processing application looks like this. So you have your data source, you have your operator where you describe how you want to process the data, and your data sink, which could also be a data stream. And if we now look at the gaming industry in particular, what kind of data streams do we have there? Well, the main data stream we have are the interactions with the game. So if you as a gamer, a player, whatsoever, use our game software and you interact with it, you create a stream of data a stream of interaction events, so to speak. So if you create a building in the game, you create a build event. If you do a quest, you get a quest event. If you fight with the computer, another player whatsoever, you get a fight event. Or if you invite your colleague, friend, then you get an invite event. And all this is tracked as JSON, for us at least, and we use our data infrastructure for that, which I would like to show you next. And be prepared, this is quite a heavy slide, but I wanted to be very transparent because this architecture is something we evolved over many years. So I'm working at InnoGames now for 13 years. That's quite a long time. And this has evolved over the past, 11 years or so. So I wanted to share this with you. Let me briefly explain it. So on the left-hand side, you can see this event client component, which is a small piece of software written in the Go language. And we use it on the game backend servers to transfer the events, so the game interaction events, to our so-called event gateway. This is the entry point to the whole data architecture. And we use JSON schema to validate the data. So we split it up into valid and invalid events. We then store it as a stream of data in our event bus, and this is also where we do stream processing. And then on the right-hand side of this slide, you can see our batch architecture, so to speak. This is all around the Hadoop ecosystem. We use everything that Hadoop has to offer and the ecosystem has to offer. We mainly use Hive for processing, but we also use Spark. We use Python and R a lot, and we use Airflow to orchestrate everything. We also recently added Google Cloud as a hybrid solution to our infrastructure, and we have a BI stack based on SQL Server. However, if we talk about stream processing, only this part is relevant. And stream processing for us means we want to react to events when they happen. And the key technologies for this are Kafka and Flink, and I would like to briefly explain the basic concepts before I show you the concrete example of customer engagement, which I brought to you today. So let's talk about Kafka first. Kafka is a distributed event streaming platform, and I mainly try to describe it not by the definition, but about what can it do for us. So the key capabilities. With Kafka, you can publish, so write, or subscribe, so read, streams of events. That means Kafka also needs to be able to store these events. And recently, well, recently is a bit wrong because this is already there for quite a while, but not in the very beginning. You can also process streams of events. So in the beginning, Kafka was just a message broker solving this broker problem that we had in data architectures, but they then also added the capability of processing the events. And as a little side note, they even took it one, introduced a full-fledged database based on the streaming data you have in Kafka. This is called KSQLDB, and you might have heard of it at this conference already, because before this session, there was another session by Helmar Becker about building an event analytics pipeline with Kafka, KSQLDB, and Druid. And if you haven't seen it, I recommend to watch it afterwards. I guess the recordings will be there. Then you can learn more about how to use KSQLDB. However, let's focus on how we use Kafka. So, in a Kafka cluster, you have many servers, and these servers are called brokers. And the data you store in Kafka, you organize them in so-called topics. We have two topics, which are events valid and events invalid. So this is already one concept. We track everything, no matter if the data is valid or invalid, but we separate it. And this turned out to be a very good idea. If you then zoom into one of these topics, you can see that they are split into partitions. And partitions are basically buckets located on the different Kafka brokers in your cluster. I will talk about this in a minute, so just keep it in mind for now. If you then zoom into one particular partition, this is split into segments, and each segment is a file on the disk of the attached broker. So one thing you have to keep in mind is for each segment, the broker, so the server, will keep up a file handle to the segment, even though the segment is already completed. So the number of partitions also influences the number of open file handles. And this is something that you should consider when choosing the number of partitions. There are also some configuration parameters to control like how big these segments are. I put them here just for reference if you want to have a look at the slide later. Now, if we want to write data to Kafka or read data from Kafka, we use producers or consumers. A producer produces messages and writes them to a topic. These messages have a key, a value, and a timestamp. For us, the key is the player ID, so the user identifier. The value is the game interaction event itself as JSON, as I mentioned before, so just a JSON string. And this, for example, is an event with name build, so someone built a building in the game. And there's also data field which contains more details about the particular event. So in this case, what kind of building did the user build? We have 1.7 billion of these events per day. So I always like to share these numbers because it gives you an idea how to configure the cluster and just to put it into perspective. Now, these events are written to the topics. And as I said, we have an events valid and invalid topic. Our valid topic has 32 partitions. Now, you might ask, is that a good number or a bad number? I don't know. Actually, choosing the right number of partitions is not that easy because you have to be aware that the more partitions you have, the more end-to-end latency you have, because committing messages takes longer. You will use more memory and you have more open file handles. And Zookeeper is also always busy with leader election if you have too many partitions. For us at InnoGames, 32 partitions works fine, but I would recommend to start with a higher number because these days Kafka is fine handling more partitions. So actually, let me check. Confluent recommends up to 4,000 partitions per broker, and I think you can go up to 200,000 partitions before Zookeeper becomes an issue. So I think 32 is okay, but I would recommend a bit more because the number of partitions also gives you a way to parallelize the processing of the data. So if we look at the consumer side, I hope you can see the little red dot here. If we look at the consumer side, we have so-called consumer groups, and these are your use cases. So each of your application has its own consumer group. And in this group, you can have any number of consumer instances. And the cool thing is that Kafka will automatically split the data between these consumers. But if you have more consumers than you have partitions, then, like in this case, if we have 33 consumers, there will be one very unhappy consumer because there's no data for it. So this is a very important decision to make how you partitionize your topic. Okay, let's have a look at this piece of software, which has, in my opinion, the greatest logo of all time. This scribble you can see over here. It's about Apache Flink. So Flink is a framework and distributed process engine for stateful computations on unbounded and bounded data streams. What does that mean? Well, first of all, in Flink, you have three main components. You have data sources, transformations, and data sinks. And you have various. And you work on unbounded streams, which have a defined start and no defined end, or on bounded streams, which have a defined start and defined end. And the fun part is that bounded streams are essentially batches of data. So it's also batch processing. So in Flink, one concept is that you unify somehow the stream in batch processing. And this is something you can then control via the APIs. Let's have a look at the APIs. So we have a high-level analytics API, and this is really cool. I will show you an example in a second or minute, let's see. Because you can describe your Flink application using SQL. And this is very powerful and makes things easier for us. Also, you can use Python, Java, and Scala, obviously, for this purpose. And then we have the data stream API, which is the most commonly used because it gives you a good level of control over what happens. But it's still rather easy to describe your streaming application. This can be used with PyFlink, so Python, Java, and Scala. And then you have the process function, which is the low-level API. It gives you control over everything. And here you use Java or Scala to describe your streaming application. I also tried Kotlin, by the way. It works. It's not officially supported, but in theory, you can also use other JVM languages if you like. Now, how does that look like by an example? Let's say you have a website, a web shop or whatsoever, and you track the clicks on your website from the user. So you have like a click stream. And what we want to do is we want to sessionize that and count the numbers of clicks per session. Okay. So using the data stream API, we have this stream of clicks and we project each click to a tuple of the user ID and the number 1 for counting. So this is how you do it in the data stream API. We then key our stream by the user ID. This is a very important concept. If you key your stream, it means that you partitionize your stream. So Flink will automatically parallelize your stream based on that. And it also means, and this is very important, it means that each worker instance will get the same key. So this is also to preserve order based on the user ID. What we then do is we apply a window function, and this is really fancy because there's a session window which looks for time gaps, and we are looking for a 30-minute time gap. And every time we see this gap, we define the sessions. And then we reduce it, sum it up, and get what we want to have. Now, if we look on this side of the slide, you can see already this looks far easier than this code over here. So this is how you do it with streaming SQL. You just select the user ID, you have an aggregation function. That means you also have a group by here, and you group it by the session window. Even though this looks very fancy and easy, you have to keep in mind that streaming SQL works different than batch SQL. So in streaming SQL, the query has to wait for data to be streamed. And it also means that the query never finishes. It continuously runs and produces records over time. The concept behind this are so-called dynamic tables and continuous queries. Dynamic tables are a logical concept. They are not always materialized, and there's more behind it, but this is the basic idea. And if you're interested in that, I recommend a talk on YouTube about real-time analytics that controls 50% of mobile network in Poland. Just look it up, you can find it there. It's a great practical example of how to use Flink SQL. However, let's continue with the next basic concept of Flink, which is state. So if we look at one event at a time in a stream of data, this is called stateless stream processing. And this could be you have a temperature sensor, you always check the current temperature, and if it's higher than a threshold, you send an alert or something. However, often we want to remember information across multiple events, and this then is called stateful stream processing. So state is a very important concept in stream processing, and almost all of the stream processing frameworks support that, and so does Flink. And in Flink, we separate keyed state and operator state. Now, keyed state is associated with a specific key. Surprise. So this could be storing the session duration or count in a streamed keyed by user, like we've seen in the example before. The operator state is bound to one parallel instance of an operator or function. And this is very special. You don't use that usually, only for source and sync functions. And it's used, for instance, to maintain the Kafka offset per partition in the source instances. Now, if we put that into a picture, this is how it could look like. So we read from Kafka these keys, A, B, C, D. In the beginning, these source functions get all of these keys, and they store the offset per partition. Then we key our stream by this key. So then we have a map instance that only gets key AB, the other one gets CD. And then, of course, this map instance on top here only stores the aggregation for AB and the other one for CD. So this is the basic difference. The cool thing in Flink is it's quite easy to work with state, and it hides its internal details. So it's really focused that you can concentrate on the business logic. Now there's one more concept, and I was thinking of adding this slide or not because it's a lot of text. And the reason I added it here is because checkpoints and save points are a concept that are often mixed up in Flink. So I read on Stack Overflow quite often the question about what is the difference, and I see a little bit of misconception often. So let me make this clear. First of all, checkpointing is based on the Chandy-Lamport algorithm, and it decouples checkpointing from processing. And it marks a point in the input stream along with the state for each operator, and it's used, and this is very important, it's used to recover from failures. So it's not meant to resume an application that was explicitly cancelled. It's made for recovering from failures. And save points are a different concept, and they are a little bit more expensive to create, and you have to create them manually. And these are if you want to stop the application and start it from a save point. So just keep that in mind, okay? And with that, I would like to jump to the concrete example, which is customer engagement. And before I start, I get your attention back by showing you this fancy animation here. And the easiest way to describe what the use case is to show you a video. So let's hope it works. Let's see. So this is a game from InnoGames called Rise of Cultures, and fighting these troops here. So down there, these are my troops. And I'm losing the fight, so I lost. I'm frustrated. I'm thinking of quitting the game, never come back. But then the system in the background detects what happened, and I go back to my city overview, which looks like this, and all of a sudden in real time I receive this, a special offer tailored for my needs. I'm very happy I can continue play the game. Now, this is of course a very simplified artificial example. This is not a real offer, so to speak, but it should show you the idea, and I think you get it. So let's have a look. How does that work? Well, I like to start with the bird's eye perspective, and then we zoom in until we reach the lowest level of detail. So let's start off with the basic concept. We have the game tracking event. I already talked about this. So we are losing the fight, which will generate a fight loss event. In fact, it generates a fight event, and it has the result down here in the data. So the result is loss because I lost the fight. That's very sad. On the other hand, we have so-called CRM campaigns. These define how we want to react to these events. A campaign can have an ID, it can be enabled or not, it's related to a specific game, it's listening to a specific event name like fight, it has a start and end date, and now the magic happens in the filter function. The filter is a JavaScript function, as you can see here. And JSON, as you might know, works very well together with JavaScript. So what we do here is we define a function that takes this event as input and returns either true or false. And only if it's returning true, we want to trigger the offer. And we evaluate this function using the Nason engine. I know in Java the Nason engine is deprecated and is removed in later Java versions. However, there's a standalone version from OpenJDK that is available on Maven Central that you can use for Java 15 and newer versions basically. Now, as you can see here, this function is simply checking if the result was loss, and if it was lost, the fight, then we will show the offer. All this goes into Flink. Flink will do the magic, evaluate everything, and then trigger the offer. This is the bird's eye perspective. Let's zoom in one time. So we have our game. The game is writing these events to the events valid topic in Kafka. This data goes into Flink, and something is happening. Ignore that something for now. We will zoom in one more level later. And then when the offer should be triggered, and this is an important concept, we write it back to another Kafka topic called CRM trigger, and the game is reading that and then reacts on that. And customer engagement therefore means to react on specific events with specific attributes to trigger an offer for the player. And this is what we call a campaign. Now, there's one important question. How can we configure the system? How can we configure the campaigns, so the rules, at runtime, which means we don't want to restart the system, redeploy, change Java code whatsoever to just change the campaigns, right? And the good thing is that stream processing has an answer for that. There is a pattern in stream processing called the broadcast state pattern. And the idea here is that we introduce another Kafka topic for configuration. This we call CRM campaigns. And this is a low frequency Kafka topic to communicate, so to broadcast the information of the campaigns to the functions that are interested. And these store this information in their state. And that way we can use that topic, and we also decoupled the configuration. So you can imagine writing to this topic, you can do it on the CLI, but you can also create a fancy front end for the CRM managers so that this is a bit more user-friendly in the end. Now, let's have a look how to implement that. So let's have a look at some actual code. First off, we have to describe the state. In our case, we use a map state descriptor, and we use an integer type for the campaign ID and the campaign, which is a POJO, a plain old Java object, as the value we want to serialize. After describing the state, we need to create a broadcast stream. We do that by reading from a special Kafka topic, and it gives us a stream of strings, JSON strings, as we have seen before. And we then use the map function to project each input campaign, each string, to the campaign pojo. And with .broadcast, we define this as a broadcast stream. You can see already that I use parallelism 1 because this is a low frequency topic and there's no need to have it parallelized. Yes, and then afterwards we need to connect it to our main event stream. So imagine you have some kind of event stream, which is the game interaction in this case, and we connect it to the campaign stream we created before. What happens then is that the follow-up process function, so this function here, which I called evaluate filter, is not a normal process function, but it becomes a so-called broadcast process function because it not only receives data from the event stream, but also from the broadcast stream. So what we need to do is we need to implement this process broadcast element function in this broadcast process function. And what I did here was to just store the campaign information we receive in the state. So this function defines how you react to broadcast updates, so to speak. And with all that, you get the broadcast state pattern. And with what we know so far, we can now zoom in one more level to the application. So let's have a look. First of all, the game, as we know, writes events to the events valid topic in Kafka. Then we read, like the fight loss event. Then we read these JSON events to Flink, and we first project the JSON string to a plain old Java object, a pojo. This is called tracking event. This is the first step. The second step is that we want to evaluate filter, so apply evaluate filter. So evaluate filter is a process function which will iterate all campaigns over all rules that we know and apply these rules to the incoming tracking event to check if there's a match, to check if we have to trigger an offer for the player. To do that, evaluate filter needs to know about the campaign. So we have this other flow which uses the broadcast state pattern, reads from the CRM campaigns topic, also maps that to a pojo, and broadcasts the information to the process function, which stores it in its state. So in its state, it knows about all the active campaigns. So every time a tracking event comes in, we can go through all campaigns and see if there's a match. If there's a match, this information is sent to the so-called trigger campaign sync. And this sync is then simply writing the information to another Kafka topic called CRM trigger. And the game reacts to these events and shows the offer to the player. Now, this is basically how it looks like. And I said in the beginning, this is called real-time customer engagement. And to be clear, the time difference between writing the events to this topic and the trigger to this topic is less than 1 second for us. Actually, it's just a few milliseconds, but let's say less than 1 second. And I have a little surprise for you. I know everyone likes surprises, especially now at Christmas times, because I created an open source version of this whole Flink application just for you. So there is a GitHub repo called Flink Realtime CRM, and this is something I will show you later. So I will also show you the link to the GitHub repo, and you can check out the code and even run it on your local machine. Now, I even have one more surprise for you, which is there's even an open source version of this left-hand side that I created just for you. Of course, I can't open source our game code, otherwise I would be in serious trouble, I would say. Instead, I created a little demo UI just for you so that you can interact with the system, and we will even have a look at this in a minute together. So this is how the system basically looks like. However, at InnoGames, we brought this to another level because we added something else. And I would like to explain what else we added to the system, which is this part over here. So what we added are the so-called segments. The idea is the following. With each incoming game interaction event, we also have a function that updates a key value store for the user or for the player. So when you buy diamonds in the game, we update the information how many diamonds you bought in real time. After evaluating the filter, we then have another thing connected to the campaign, which is called the segment. And with the segment, you can define which groups of players are eligible for the offer. And this could be like the player must have bought at least 100 diamonds. That way, you can not only define to which game interaction you want to react and show an offer to the player, but you can even say which groups of players are eligible for this. And with all that in mind, it's time to wake you up again with a fancy animation and show you a live demo. And please keep your fingers crossed. It's a live demo on a conference presentation. I decided to not pre-record the video, so let's see if that was a good idea or not. But okay, so let's start off with Docker. So I'm running Docker on my local machine so that I have a Kafka broker and Zookeeper. So this is the minimal setup to have Kafka running. And then I have two projects. So one is the Flink application. This is how it looks like. And like I said, this is open source. You will get the links later, I hope. It's part of the slides, actually. And this is how it looks like. So I added comments to also explain what I'm doing here. And basically, there's a bit of configuration going on. This is where I create the broadcast stream. You saw it already on the slides. And this is how I create the main input stream of events for the game interaction. And this is basically here the full stream that I have. So this is my pipeline. This is where I describe my pipeline. I have my event stream, I connect it to the broadcast stream, and I have the process function. We can also look at the process function itself. So there are two main things that it has to do. First of all, you have to describe how to deal with incoming events. In our case, we get the campaigns from the state, we iterate over each campaign, and then we check if this incoming game interaction event matches with one of these campaigns. The other thing we need to do is, like I described earlier, we need to describe how to deal with broadcast elements, so with updates through this broadcast topic. And this is rather simple because we just store the information on our state, and that's already it. The trigger campaign sync, so the last element in the stream, is then just sending the information to the Kafka topic. That's even simpler. Because whenever there's a match, we send this information to the sync. And now let's start the Flink application and hope it works. What I can tell you, there's a nice little trick I didn't know before, which is if you start your Flink application locally like this, so with create local environment with web UI instead of get execution environment, then you get the Flink UI on your local machine, and I can also show it to you. So Flink has a nice UI which you can use to check your running Flink application. This is how it looks like, and this is the pipeline I just showed to you. And here you can see this is how it looks in Flink. So we have our broadcast stream over here, and we have our normal event stream over here, and both go into this evaluate filter. One thing you can see already, Flink will group together operators in your stream if it makes sense. So in this case, it grouped together the evaluate filter function and my trigger campaign sync together. Okay, now the second part of the demo is the UI, and I don't go into too much detail here because this is a basic Spring Boot application, and I just created it so that you have something to play around with to make it a bit more visual, I would say. So let's just start it right away. It's a Spring Boot application running on port 7071, and it talks to my local Kafka cluster. Okay, let's switch back to the browser and go to localhost 771. This is how it looks like, and I'm not a front-end developer, but I hope it still looks okay-ish, and I hope you get the idea. So the first thing that happens is that the CRM manager, they write the campaign definition to Kafka, which is then processed by Flink. Of course, in the real world, they don't just write the JSON. They have a fancy UI to do that, but we use JSON in this case. So we have this campaign, and as you can see, it's just checking for fight events, and it checks if the result was loss. So send it to Kafka, and hopefully Flink is now aware of it. Now we are playing the game on our mobile device, in our browser, whatsoever, and we generate data while playing the game. And let's say we're having a fight in the game and we are losing it. So this would generate an event like this. We have a fight event and the result is loss. We defined a campaign to react on this. So if I send this to Kafka, something should happen. And to visualize that, I have this little window here on the right-hand side. But let's see if it works. Yay. That's good. So on the right-hand side, you can see what happened. Flink detected that there was a match between the game interaction and the campaign, and it sent the information to the other Kafka topic, which triggered this little pop-up over here. So this is just an example. Imagine that this could be an offer in the game. By the way, it doesn't have to be an offer. So this is not only about monetization. It could also be something like showing you a specific tutorial or quest to make you understand specific game logic in a better way. So it's overall to improve, just like I said in the beginning, with the halo effect, to improve the first session, but also the later experience of the game. Now, if I generate this example again, and I change the result from loss to win, and I send it to Kafka, nothing should happen because I won the fight, right? Nothing happens. What we can do now, we can update the rules. So I generate this example again, use the same campaign ID, so I overwrite the campaign, and I now change the filter function to not check for result loss, but for result win. And I sent this to Kafka, and this updated the campaign. If I now generate this example and change the result back to win, and I send it to Kafka, now something should happen. Yes, and it did. That's cool. So this was the live demo. As I said, both of these projects are open source on GitHub. You can check them out later. Okay, let's jump back into the presentation to wrap it up a bit and to give you also a future outlook. So let's have a look at the future era. What else can you do with this? Well, one disclaimer, this is now something that is just existing in my head. This is nothing we implemented at InnoGames yet, in theory. So let's have a look at the system again. What we could do is we could add a little bit of machine learning to the system. We can do that by using a centralized feature store like Hopsworks, which is an open source machine learning storage. And what we can then do is we can also broadcast machine learning models that were trained in batch. We can use some serialization format like JPMML for this use case, and we use the broadcast state pattern so that the functions get these models and then they store it in their state. Now, what we then do is we use this update function over here to update the features in real time in the feature store. And then later, when we evaluate the segment, we get the up-to-date feature vector for the current player from the feature store. And we basically predict in streaming. That way, we get real-time predictions. And we could also do something like, okay, you lost the fight, but how likely is it that you leave the game? So we calculate some kind of churn score in real time, and then you only get the offer if it's likely that you churn, so that you leave the game. And this is quite powerful. And why did I choose Hopsworks here? Because Hopsworks has an integration for Flink, which is quite fancy, because what you can do is you can just create a data stream like this and insert the stream into the feature store. So it's natively supported. This is now a complete different example. It's about Ethereum prices, so complete different context, but it should give you the basic idea. Okay. And with that, I hope you are a little bit inspired. And if you take out one thing of the conference, I like to connect it to the very beginning. Keep in mind that live doesn't happen in batches, and it's very valuable to also think about stream processing use cases, because stream processing often is just connected to analyzing data, showing some dashboards, but I hope by this example you saw that you can also have some operational systems based on that. Yeah, thank you very much. There's one more thing though that I'd like to share, like promised. These are the links to GitHub. So these two repositories, feel free to check them out. I'm also active on LinkedIn. I'm very happy if we can connect. If you liked the talk, also feel free to tag me in a post. That would be cool. And yeah, even one more thing, sorry, because, you know, I'm a gamer. I like retro games, and one thing I really liked about gaming was that there were always these hidden levels in the game, these bonus levels. And so if you get the slides afterwards, I also have some bonus level for you in this presentation. I have some bonus slides, and on these bonus slides I have many details about the Flink learnings I got while implementing that. So like how to configure stuff, how to use the Flink UI, some other learnings for debugging, and so on and so forth. So there's also details about the Flink runtime, and all that is part of these bonus slides that you can check out later. But with that, I would like to say thank you one more time. It was a pleasure to be here, and also thanks for the conference, for the organizers, for all the effort, and let's